An amateur astronomer in his backyard just captured something that shouldn't be there. 5 points of light, arranged in a perfect ring, around an object that came from another star system. Ray's telescope wasn't expensive, his processing wasn't professional, but his images of 3i ATLAS show a formation so geometric, so eerily coordinated, that even scientists are struggling to explain it away as dust or diffraction. Some call it artifact, others whisper about escorts, and NASA, which usually releases data within days, has gone unusually quiet. Stay with me. Tonight we're going to walk through every frame, every anomaly, every impossible detail that makes this the strangest interstellar visitor we've ever seen, because something is moving around that comet. And we need to figure out what it is before it's gone. If you're feeling what I'm feeling, that pull toward unanswered questions, hit subscribe so you're here when the next piece falls into place. Drop a comment with where are you watching from, what time it is there, and what you think about this new development. Thanks for being part of this community. Part 1. The 5-point formation. What Ray actually captured. You're scrolling through your feed late at night when you see it. 5 points of light, perfectly spaced, glowing around something that shouldn't be there. The image is grainy, over-processed maybe, but the pattern stops you cold. Someone in the comments writes, "This isn't natural." Another responds, "We're not alone." A third, more cautious, "It's just diffraction." But you can't look away, because deep in some primal part of your brain, symmetry means intelligence, patterns mean design. And this pattern, circling an object from beyond our solar system, looks too perfect to ignore. This is Ray's footage. An amateur astronomer with decent equipment and a passion for hunting faint objects decided to point his telescope at 3i/ATLAS, the latest interstellar visitor to pass through our cosmic neighbourhood. What he captured has divided the internet, confused optical scientists, and created a mystery that NASA still hasn't addressed. So let's break down what Ray actually recorded, what it could mean, and why even the skeptics are having trouble explaining it away. Ray isn't working with Hubble. His setup is what you'd find in the garage of any serious amateur astrophotographer. An 8 to 14-inch Schmidt-Cassegrain telescope, a standard RGB sensor, no infrared or ultraviolet filters, equipment that thousands of people own, nothing exotic. He pointed it at 3i/ATLAS on a clear night, captured multiple frames, and began the tedious process of stacking them to reduce noise and bring out faint details. Standard procedure. The kind of thing amateurs do every night across the world. Except this time something appeared that wasn't supposed to be there. In the raw, unprocessed frames you can barely see it. The object itself is a fuzzy blob, typical for a comet with an active coma, the cloud of gas and dust surrounding its nucleus. Background stars streak slightly due to tracking imperfections. Nothing unusual. But when Ray began stacking and sharpening those frames, 5 bright points emerged from the noise, arranged in a rough circle around the comet's core. Not random, not scattered, arranged, and they persisted across multiple captures, separated by minutes. If these were just hot pixels or sensor noise, they would appear randomly, flickering in and out. Instead, they remained coherent. They stayed in formation. Let's talk about what can create bright spots around an astronomical object. Diffraction is the obvious culprit. Light bending around the edges of telescope optics can create rings, spikes, patterns. Every astronomer knows this. Point a telescope at a bright star and you'll see a characteristic pattern based on your telescope's design. But here's the problem. Diffraction patterns depend on the angle of incoming light. They shift as the telescope tracks. They change shape if the object moves relative to the optical axis. The 5 points in Ray's images don't behave that way. They persist. They remain roughly equidistant. And while diffraction can create rings, it doesn't typically produce 5 distinct bright nodes spaced evenly around a moving, outgassing object. Background stars are the next suspect. Maybe Ray's tracking was off, and stars smeared into arcs that just happened to fall around the comet. Except the timescale doesn't work. Ray's exposures were short enough that stars appear as points or very slight streaks. And stars don't orbit. They don't appear to circle an object. They drift in straight lines relative to the field of view. The 5 points don't behave like stars. Here's where it gets interesting. Ray didn't just capture one moment. He captured several sequences over about 30 to 40 minutes. And in those sequences, the 5 points shift slightly. Not dramatically. Not in ways that scream objects in orbit. but they change position relative to each other and to the comet's core. Frame 20 shows them in one configuration. Frame 14 shows them rotated slightly. Frame 9 shows them shifted again. If you were watching this happen in real time, you'd swear something was moving, something was circling. And that's what has people spooked. Stacking can create illusions. When you layer multiple images on top of each other, random noise averages out, but consistent features get reinforced. If there's a real structure in the coma, maybe jets pointing in specific directions, stacking will make them pop. But stacking can also amplify artifacts. A hot pixel that appears in the same spot across multiple frames becomes a bright point in the stack. A faint background galaxy that happens to align with the comet's path becomes a false companion. Ray's stacking process introduced consistency, which is good for signal, but can create the illusion of structure where there's only chaos. Optical scientists are split. Some look at the images and see exactly what you'd expect from dust jets combined with imperfect processing. Comets eject material unevenly. A nucleus rotating with active vents can produce bright clumps of dust that scatter sunlight. From certain angles, those clumps can appear to surround the nucleus. Add sharpening algorithms that exaggerate edges, and you get something that looks geometric. Artifact cluster, they call it. Nothing to see here. But others aren't so sure. The spacing bothers them. Even with generous assumptions about projection effects and dust dynamics, getting 5 roughly equidistant bright nodes is statistically weird. Not impossible, just weird. And the minute-scale evolution bothers them even more. Because here's the thing. If these are just dust clumps in the coma, they should disperse. The coma is an expanding cloud. Material doesn't orbit. It flows outward, pushed by solar radiation and the comet's own outgassing. Anything in the coma should be drifting, spreading, dissipating. But Ray's 5 points remain coherent across tens of minutes. They shift, yes, but they don't dissolve. They don't blur into the background haze. They persist. And persistence implies structure. It implies something holding those bright regions in place. Maybe it's the geometry of the jets themselves, constantly replenishing those positions. Maybe it's a trick of perspective. Or maybe, just maybe, it's something else. The public reaction has been predictable. Online communities exploded. Conspiracy channels lit up. The phrase "too perfect to be random" appeared in hundreds of comments. People started calling them escorts. Some suggested probes. Others went further, proposing that 3I/Atlas isn't a comet at all, but something masquerading as one. The speculation spiraled. But underneath the noise, there's a legitimate question that even careful scientists are asking. What configuration of natural processes produces this pattern? And why does it look so much like something maintaining a perimeter? We're going to dig into rotation anomalies next, into the bizarre spin that complicates every explanation. We're going to examine the jet geometry that makes no sense under standard comet physics. We're going to look at hidden details in the metadata that Ray didn't even notice. And we're going to ask the question that nobody at NASA is answering yet. If this is just a comet, why does it look like it brought friends? Part 2. The rotation. Nobody can agree on. Comets spin. That's normal. They're irregular chunks of ice and rock tumbling through space, heated unevenly by the sun. As frozen material vaporizes, jets push asymmetrically on the nucleus, inducing rotation or changing it over time. Most comets rotate slowly, with periods measured in hours or even days. You watch them over weeks, tracking subtle changes in brightness and coma structure. Building a picture of how they're oriented and how fast they're turning. It's methodical work, patient work. Which is why what Ray observed in less than 2 hours is so strange. Because 3I/Atlas appears to be spinning fast. Very fast. And the way it's spinning doesn't quite fit the script. Let's start with the basics. Ray noticed something odd while reviewing his captures. The comet's coma, that fuzzy cloud of dust and gas, wasn't static. Over intervals of 60 to 90 seconds, the density distribution shifted. Brighter regions rotated. Fainter areas emerged. It looked like the object was turning, presenting different faces to his telescope. If you've ever watched a lighthouse beam sweep across the sky, it's a bit like that. The source doesn't move, but the beam does, and what you see changes. Except in this case, the comet itself seemed to be the rotating source, and the beams were jets of material erupting from its surface. Here's where it gets complicated. Ray's camera, like most astrophotography setups, can introduce mirror flips depending on the optical path. If you're using a diagonal or, Certain types of correctors, the image gets flipped horizontally. So when Ray looked at his images, the rotation appeared clockwise in some and counterclockwise in others, depending on how the image was oriented. That's expected. That's normal. But when you correct for the mirroring and track the actual motion of features in the coma, a pattern emerges. The object is rotating. And it's doing so in a way that suggests a surprisingly short period, possibly just minutes. That's not typical for a comet nucleus several kilometers across. Most comets rotate slowly because they're large enough that their structural integrity limits how fast they can spin without flying apart. The forces generated by rapid rotation would overcome the weak gravity and mechanical strength holding the icy rubble together. A comet spinning with a period of a few minutes would be under enormous stress. It's not impossible, especially if the object is small or unusually strong, but it raises questions. And the questions multiply when you look at specific frames. Frame 20 shows a bright core with a slight asymmetry pointing in one direction. Frame 14, captured about 6 minutes later, shows that a symmetry rotated roughly 30 degrees. Frame 9 shows it shifted again. If you map these changes onto a rotation curve, you get a period somewhere between 15 and 25 minutes. Fast. Uncomfortably fast. But maybe it's not pure rotation, maybe it's precession. Imagine a top wobbling as it spins. The axis itself rotates, creating complex motion that can make surface features appear to move in strange ways. Comets can precess, especially if they're outgassing asymmetrically. The jets act like tiny rocket engines, pushing the nucleus off balance, inducing wobbles and tumbles. If 3I/ATLAS is precessing rapidly, that could explain the minute scale changes Ray observed. It could also explain why the changes seem too stable to be random. Precession has structure, it has periodicity, and periodicity can look intentional, even when it's not. There's another possibility. Rotational wobble driven by outgassing torque. When material jets off a comet, it carries momentum. If the jets are active on one side and dormant on the other, they create a torque that spins the nucleus or changes its spin rate. This is a known phenomenon. Missions like Rosetta observed it on Comet 67P, watching the nucleus slowly change its rotation over months. But 3I/ATLAS seems to be changing much faster, over minutes, not months. That implies either very strong outgassing or something else affecting its motion. Or maybe it's all an artifact. Imperfect tracking can make a stationary object appear to rotate. If Ray's telescope wasn't perfectly following the comet's motion across the sky, the coma would drift slightly in the frame. Features would shift position. And when you stack those drifting images, you can create the illusion of rotation where none exists. The technical term is field rotation, and it's a common issue in astrophotography. Except Ray's star field doesn't show the same drift. The background stars remain crisp. Their positions are consistent. If field rotation were the culprit, the stars should show it too. They don't. This is where the conspiracy theorists started paying attention. Because if 3I/ATLAS is rotating rapidly, and if that rotation is stable rather than chaotic, it starts to resemble something familiar. Spacecraft. Satellites. Objects designed to maintain orientation. Controlled attitude adjustment, they call it in aerospace engineering. When you want a spacecraft to point in a specific direction, you spin it up or use thrusters to stabilize it. The rotation Ray observed looks too stable, too regular, to be a tumbling chunk of ice. It looks like something maintaining control. Now, to be clear, there's no evidence of artificiality. None. But the pattern invites the comparison. And once that comparison enters the conversation, it's hard to shake. Real physics offers explanations for apparent spin reversals and rotational illusions. Frame aliasing is one. If you're sampling a rotating object at intervals that aren't perfectly synchronized with its rotation period, you get what's called the wagon wheel effect. You've seen it in movies. A wheel spinning forward looks like it's spinning backward because the camera's frame rate doesn't match the wheel's speed. The same thing can happen in astronomy. If Ray's exposures were spaced just right, or just wrong, the rotation could appear to reverse or stutter. It's an illusion, but a convincing one. Then there's the question of how the rotation connects to the 5-point anomaly. If both features are real, they might be linked. Imagine a nucleus with 5 active vents spaced evenly around its equator. As it rotates, each vent fires in sequence, creating bright pulses of dust that appear to orbit the object. From a distance, you wouldn't see individual jets. You'd see bright points maintaining position relative to the nucleus, moving as it turns. That's a natural explanation. It fits the physics. But it requires an almost perfect arrangement of vents, which brings us back to the same problem. Why is it so symmetric? Why does it look designed? NASA hasn't commented on rotation parameters yet. No official spin period. No analysis of precession or wobble. The silence is conspicuous. Usually, when an interstellar object shows up, the agency releases preliminary data quickly. Orbital elements, brightness curves, rough size estimates. But with 3I/Atlas, the usual flow of information is slowed. Maybe they're waiting for more data. Maybe they're checking and rechecking their models. Or maybe they're seeing the same weirdness Ray captured and trying to figure out how to explain it without sparking another Oumuamua-level media frenzy. Because the last time an interstellar visitor behaved strangely, the explanations got exotic, fast, and nobody wants that headache again. So we're left with a comet that spins too fast, too smoothly, with features that shift in ways both regular and strange. We're left with questions about torque and wobble, and whether any of it connects to those 5 bright points. And we're left wondering if the rotation is a clue or a distraction, a key to understanding the anomaly, or just another layer of confusion piled on top of an already baffling object. Next, we'll look at the jets themselves, at the geometry that breaks the rules, and at why the symmetry makes no sense, yet. Part 3. Jet geometry, shadowing, and why the symmetry makes no sense. Comets are messy. That's the first thing you learn when you start studying them. They're not smooth spheres with orderly processes. They're jagged, irregular bodies pockmarked with pits and fractures, coated in dusty lag deposits, riddled with volatile pockets that heat unevenly as they approach the sun. When those volatiles vaporize, they don't erupt uniformly. They blast out from localized vents, creating asymmetric jets that twist and spiral as the nucleus rotates. The result is chaos. Beautiful, dynamic chaos. No two comets look the same. No single comet looks the same from one week to the next. So when you see a comet with repeating symmetric structures in its coma, your first thought should be skepticism, because nature doesn't do symmetry. Not like this. Not usually. Let's set the stage with what we know from previous interstellar visitors. 1I/Oumuamua, the first confirmed interstellar object, barely outgassed at all. It showed non-gravitational acceleration, suggesting some kind of material release, but we never detected a visible coma or jets. It moved like something was pushing it, yet left no obvious trail. 2I/Borisov, the second visitor, was the opposite. Strong activity, a bright, expansive coma, clear evidence of carbon monoxide outgassing, jets that shifted and flickered as it tumbled through the inner solar system. Chaotic, asymmetric, exactly what you'd expect from a comet. Neither of them showed anything like what Ray captured from 3I/Atlas. Neither of them had bright nodes arranged in a ring. Neither of them looked coordinated. Ray's footage, though, shows something different. The 5 bright points don't just exist, they align with structures in the coma. If you enhance the contrast and trace the faint streamers of dust, you see radial patterns extending from the nucleus, and those patterns intersect with the bright nodes. It looks like jets, multiple jets, firing simultaneously, each one creating a bright region where dust scatters sunlight most efficiently. But here's the problem. Simultaneous activation of 5 equidistant jets shouldn't happen naturally. Comets don't have evenly spaced vents. Their geology is random, shaped by accretion, collisions, and uneven heating over billions of years. Finding 5 active regions spaced 72 degrees apart is statistically unlikely. Not impossible, but unlikely enough to make you wonder. Real scientific explanations do exist. One possibility is axis-aligned dust vents. If the comet's rotation axis happens to be oriented just right relative to the Sun, and if there are vents clustered near the equator, they could activate in sequence as the nucleus turns, creating the illusion of simultaneous jets. From our perspective, we'd see all 5 lighting up at once, even though they're firing one after another. It's a projection effect, a trick of geometry. The same way a rotating lighthouse beam looks constant if you're standing in the right spot. This explanation works mathematically, it fits the physics, but it requires a very specific alignment and a very specific vent distribution. Coincidences pile up. Another idea involves resonant structural features. Imagine a nucleus with internal cracks or layering. shaped by thermal stress cycles over eons. As it heats up near the Sun, those cracks could channel gas in predictable directions, creating repeating patterns. Some asteroids show similar behaviour. Their spin rates can lock into resonant states where features repeat in symmetric ways. If 3I/Atlas has internal structure that promotes this kind of resonance, the jets could appear organised without being artificial. They'd be following natural pathways carved by geology, just in a way that happens to look regular. Again, possible. Again, requiring very specific conditions. Then there's grain size distribution. The dust in a comet's coma isn't uniform. Some particles are large, some are microscopic. They scatter light differently depending on their size. Large grains forward scatter more efficiently. Small grains backscatter. If the comet is ejecting dust with a particular size distribution in specific directions, you could get bright nodes that look artificially arranged, but are really just wavelength-dependent scattering effects, amplified by observation geometry. This is a known phenomenon. It's been observed in other comets, but usually it creates gradients, not discrete points. Usually it's subtle. What Ray captured isn't subtle. Let's talk about the shadowing. In several frames there are dark ridges in the coma, not just dim regions, dark, as if something is blocking the light. Shadows imply structure. They imply something solid enough to cast a silhouette. In a diffuse cloud of gas and dust, you don't expect sharp shadows. Everything glows and scatters. But if there's a more rigid underlying shape, maybe a fractured nucleus with large distinct lobes, those lobes could create shadow zones as they rotate. Rosetta saw this on 67P. The rubber duck shape of that comet cast shadows across its own surface, creating dramatic contrasts. 3I/Atlas could be similar. A weird shape, rotating, casting shadows through its own coma. That would explain the dark ridges. It would also explain why those ridges shift between frames. The nucleus turns, the shadow moves, the pattern changes. Simple, except the shadows don't behave quite right. They shift, yes, but they also seem to track with the bright points. Where there's a bright node, there's often a corresponding dark ridge nearby, as if the two are linked. That's harder to explain with simple shadowing. It suggests some kind of organised structure in the coma itself. Dust lanes, maybe. Regions where material is clumped together, creating both bright reflections and dark gaps. Or maybe it's a digital artifact. Heavy sharpening can create dark halos around bright objects, mimicking shadows where none exist. Ray's processing included aggressive sharpening to bring out faint details. That could be the source. But then why do the shadows appear in the less processed frames too? Stacking amplifies radial symmetry. That's a fact. When you overlay multiple images of an object with any kind of rotational motion, patterns that repeat tend to reinforce. Random noise cancels out. Consistent features get brighter. If there's any inherent symmetry in the comet's jets, even weak symmetry, stacking will exaggerate it. It's like applying a filter that prefers order over chaos, and humans looking at the result will latch onto that order because we're wired to see patterns. We see faces in clouds. We see constellations in random stars. We see design in noise. So maybe Ray's images are just revealing our own cognitive biases, showing us what we want to see rather than what's really there. But what if the nucleus itself is polyhedral? Some asteroids are faceted, shaped by collisions into vaguely geometric forms. If 3I/Atlas is a fractured body with flat faces and sharp edges, its rotation could create repeating patterns as different faces point toward the Sun. Each face would heat differently, activating different vents, producing jets that appear in sequence but maintain a symmetric arrangement. A tumbling cylinder could do something similar. As it spins, the same features come around again and again, creating periodicity. Or maybe it's a binary system. Two bodies orbiting each other, each contributing to the coma, creating a pattern that looks like a single object with escorts. That would explain a lot. But there's no evidence of a binary. No periodic brightness variations that you'd expect from mutual eclipses. No gravitational wobble in the trajectory. The speculative angle that keeps creeping in is this. Could the shape be engineered? Could those 5 jets be nozzles? Could the rotation be controlled? It sounds absurd until you remember that we've sent probes beyond the solar system. Voyager, Pioneer, New Horizons. Objects that maintain orientation using thrusters and spin stabilization. If we can do it, why couldn't someone else? Something else? It's pure speculation. There's no evidence. But the geometry keeps inviting the question, why is it so symmetric? Why does it look so much like a designed configuration? And why, when you try to explain it with natural processes, do you keep needing special conditions, perfect alignments, and convenient coincidences? Ray's metadata is hiding more clues, details he didn't notice, anomalies in the starfield, colour shifts in the coma, micro movements that shouldn't exist if this is just a comet. We'll dig into those next. We'll look at what the data itself is trying to tell us, buried beneath layers of processing and assumption. Because if there's something strange happening with 3i/Atlas, the answer might not be in what we can see, it might be in what we almost missed. Part 4, Hidden Metadata, what Ray forgot to mention. But the frames reveal. Every image carries secrets. That's something professional astronomers know well. The picture you see, the glowing nebula or distant galaxy or faint comet, is just the surface. Underneath, embedded in the file itself, is a second layer of information. Exposure times, sensor temperatures, timestamp data, tracking coordinates, and buried even deeper in the actual pixel values and the relationships between frames are clues that can reveal whether what you're looking at is real or artifact, natural or impossible. Ray's images of 3i/Atlas are no exception. On the surface, they show 5 bright points and strange rotation. But in the metadata, in the details he didn't highlight and maybe didn't even notice, there are hints of something stranger. Not proof, not yet, but hints. And sometimes hints are more unsettling than answers. Start with the star streaks. When you're doing astrophotography, your telescope tracks the sky, compensating for Earth's rotation so your target stays centered. If the tracking is perfect, stars appear as points. If it's imperfect, they smear into short lines. Every amateur deals with this. It's normal. Ray's images show star streaks, as expected. But if you look closely, some of them are bent. Not dramatically, not in ways that scream something's wrong, but bent, curved. As if the tracking speed changed mid-exposure, or as if the stars themselves moved in arcs rather than straight lines. That shouldn't happen. Stars move linearly relative to a tracking telescope. If the tracking is off, the streaks should be straight, just angled wrong. Curved streaks suggest either non-uniform tracking, which would require a serious mechanical fault, or micro-movements of the object being tracked. Movements inconsistent with normal comet motion. Comet positions are predictable. They orbit the Sun. Their paths are smooth curves governed by gravity, with tiny perturbations from outgassing. Those perturbations are measurable but small. They don't cause sudden jerks or oscillations. They nudge the comet gently over days or weeks. So if 3i/Atlas were wobbling or shifting position rapidly enough to bend star streaks, that would be unusual. Very unusual. It would imply forces acting on the object that aren't in the standard models. Solar radiation pressure can't do it. Outgassing torque would need to be absurdly strong. And gravitational interactions with anything nearby are ruled out because there's nothing nearby. No planets, no asteroids, just empty space. Yet the star streaks curve. And that's a problem. Next, the colour gradients. Ray's setup uses an RGB sensor. Red, green and blue pixels arranged in a grid, each recording different wavelengths. When you combine them, you get a full colour image. Comets typically show colour variations based on dust composition and grain size. The coma can be reddish near the nucleus where larger particles dominate, fading to bluer tones further out where smaller grains scatter sunlight more effectively. That's expected. What's not expected is sharp transitions, distinct blue-green zones that don't blend smoothly. Ray's images show exactly that. Patches of coma with colours that look wrong for a purely RGB setup, observing reflected sunlight. They're too saturated, too distinct, almost like emission lines, the kind you'd see if specific gases were fluorescing. But Ray wasn't using narrowband filters. He wasn't isolating specific wavelengths. So where are these colours coming from? One explanation is sensor noise. Digital sensors produce artifacts, especially at high ISO settings or long exposures. Hot pixels glow brighter than they should. Cold pixels drop out. Bayer matrix interpolation can create false colour gradients where none exist. If Ray's sensor was noisy, and if his processing amplified that noise, the colour zones could be entirely artificial. But noise tends to look random, grainy, chaotic, These zones have structure. They align with the bright points. They follow the coma geometry. That suggests they're not pure noise. They're responding to something real in the image. Maybe dust with unusual composition. Maybe contamination in the optical path. Or maybe something in the coma genuinely emitting light in ways we don't expect from a typical comet. Ray's stacking strategy is another piece of the puzzle. He didn't just average his frames, he cropped them tightly around the comet, aligned them precisely, and applied variable sharpening. Light sharpening to preserve overall structure, heavy sharpening to bring out faint details. Then he adjusted contrast curves, brightening the dim regions and compressing the bright ones to fit a viewable range. Every step is standard. Every step is defensible, but every step also introduces the risk of amplifying artifacts. Sharpening can turn faint sensor noise into apparent structure. Contrast adjustments can make random fluctuations look like coherent features. Alignment errors, even tiny ones, can create ghost images that seem to orbit the target. Stacking is powerful, but it's also dangerous if you're not careful. And Ray, like most amateurs, was focused on making the image look good, not on forensic accuracy. 3. Frames in particular have attracted attention. They show what look like fireball-like tails trailing the object. Not the smooth, diffuse tail you'd expect from a comet. Discrete, almost clumpy structures extending behind the nucleus. Some researchers have suggested these are jet backflow, material ejected forward that then gets caught in the solar wind and swept backward. Others point to dust clumping, a process where particles collide and stick together, forming larger aggregates that reflect more light. Both are possible. Both happen in real comets. But both are usually chaotic. The tails in Ray's images look too organised, too linear, like something being dragged behind a moving object rather than naturally dispersing into space. Sharpened, blooming artifacts are another candidate. When you sharpen an image, you enhance edges by increasing the contrast between adjacent pixels. If there's a bright object in the frame, sharpening can create halos or streaks radiating from it. These artifacts can look remarkably like real tails, especially in faint, noisy images. Ray's aggressive sharpening could easily have produced them, except the tails appear, at least faintly, in the less processed versions too. They're not purely a product of sharpening. They're there in the raw stacks, dimmer, less distinct, but there. Oscillatory motion is another concept worth exploring. If 3i/Atlas is rocking or yawing, nodding its axis back and forth as it rotates, that motion would create repeating patterns in stacked images. Features would appear to pulse or shift rhythmically. Over multiple frames, that rhythm would build up, creating what looks like structure even if the object itself is chaotic. Spacecraft experience this. When a probe's attitude control isn't perfect, it wobbles. The wobble is periodic. It shows up in telemetry. For a comet, the same principle applies if outgassing is creating uneven torque. The nucleus rocks. The jets sweep back and forth. And from a distance, the whole system looks like it has internal order. It's an illusion born from repetition, but it's a convincing illusion. Professionals reviewing Ray's footage have used an interesting phrase: consistency in inconsistency. What they mean is this: the anomalies aren't random. The bright points don't flicker in and out arbitrarily. The colour zones don't shift chaotically. The curved star streaks don't appear in random frames. There's a pattern to the weirdness, and patterns suggest underlying causes. Whether those causes are artifacts of imaging and processing, or real physical phenomena, is still unclear. But the fact that the strangeness repeats, that it has structure, means it's not just noise, it's signal. The question is, signal of what? Amateur equipment can produce micro-artifacts that mimic escorts. Hot pixels can cluster. Lens flares can appear in formation. Diffraction spikes can align in misleading ways. Every astronomer who's spent time imaging faint objects has been fooled at least once by something that looked real but wasn't. The field is full of cautionary tales, bright spots that turned out to be cosmic ray hits, galaxies that were sensor glitches, objects that moved between frames because the telescope bumped. Skepticism is warranted, but so is curiosity, because if the microshifts in Ray's data are real, if the object genuinely wobbled or changed orientation, or had material moving in ways not explained by standard comet physics, then we're looking at mass redistribution, or jet torque far stronger than expected, or, in the most speculative scenario, something controlling its motion. NASA's silence grows louder with each passing day. Ray's footage went viral almost immediately. Within 48 hours it was everywhere. Forums, social media, news aggregators. The agency must have seen it. They must have tasked Hubble or JWST or at least ground-based observatories to take a look. But no official statement, no preliminary data release, no reassuring press conference explaining the anomalies as artifacts or natural phenomena, just silence. And that silence is fertilizer for speculation. Because if there's nothing to see, why not just say so? Why not release images showing a normal comet with normal jets and put the whole thing to rest? Unless, of course, their images show something similar. Unless they're seeing the same pattern Ray captured. Unless they're trying to figure out how to explain it without triggering a media circus. The timing is suspicious, and suspicion, once planted, grows fast. What do they already know? That's the question keeping people up at night. Do they have spectroscopy data showing unusual composition? Do they have high-resolution imaging revealing structure in the nucleus? Do they have radar returns indicating unexpected shape or rotation? Or do they have exactly what Ray has, just clearer, and they're staring at it the way we are, trying to decide if the universe just handed them something extraordinary, or if they're about to be embarrassed by an artifact? We don't know, and not knowing is worse than almost any answer. Next, we'll examine the pre-NASA tension, the timing, the delays, the withheld data. Because if this mystery is going to break open, it'll start there, in the silence, in what they're not saying, in the gap between observation and explanation where possibilities multiply unchecked. Part 5. Pre-NASA tension. What the agency knows but hasn't said. There's a rhythm to how space agencies release information. You spot something interesting. You task a telescope to observe it. You collect data. You run preliminary analysis. You write a brief summary. You hold a press conference or issue a statement. The whole process, from observation to announcement, typically takes days, maybe a week if the data is complex or requires peer review. But you say something. You give the public a morsel, a confirmation that you're looking, that you're on it, that science is happening. It's good public relations. It reassures people that experts are in control, that the universe, however strange, is being monitored and understood. So when NASA goes silent when the rhythm breaks, people notice, and they start asking why. Ray's footage spread fast. Within 48 hours of his initial post, it had been shared thousands of times. Within 72 hours, mainstream science outlets were covering it. Amateur astronomers around the world were pointing their telescopes at 3I/Atlas, trying to replicate his observations. Some succeeded. Some saw hints of the same pattern. Others saw nothing unusual. The inconsistency fueled debate. But the one voice conspicuously absent was NASA's. No tweet, no blog post, no preliminary statement saying, "We're aware of the amateur footage and are investigating." Just silence. And that silence, in the age of instant communication, feels deliberate. Normally, NASA is prompt. When Oumuamua showed up in 2017, the agency released data within days: orbital parameters, preliminary size estimates, reflectivity measurements. When Borisov appeared in 2019, same thing. They confirmed its interstellar origin almost immediately and provided regular updates as it passed through the inner solar system. They were transparent. They were engaged. The public felt included in the discovery process. With 3I/Atlas, though, something is different. The object was detected. Its interstellar trajectory was confirmed. Then, quiet. A scheduled briefing was announced, then postponed, then rescheduled, then postponed again. Officials cite ongoing analysis and data calibration, standard excuses. But those excuses ring hollow when amateur astronomers are capturing and sharing images in real time, and the agency responsible for some of the most powerful telescopes ever built has nothing to show. Internal chatter, if you believe the rumours, tells a different story. People who claim to have connections inside the Jet Propulsion Laboratory or the Space Telescope Science Institute whisper about early Hubble stacks showing structural anomalies in the inner coma. Features that shouldn't be there. Patterns that match what Ray captured, but with higher resolution and better signal-to-noise ratios. These are rumours, understand, unconfirmed, the kind of thing that spreads on forums and in private messages between enthusiasts who know people who know people. But the rumours persist, and they're specific enough to be either true or very carefully fabricated. They mention image processing pipelines detecting geometric structures. They reference internal emails discussing whether to classify certain observations as artifacts pending further review. They describe meetings where scientists debate how to present findings without triggering immediate speculation about artificiality. There's no evidence of actual secrecy, no smoking gun, no whistleblower, leaking classified images. NASA operates transparently most of the time, bound by policies that require public access to publicly funded data. But those policies have caveats. Data can be withheld temporarily if releasing it prematurely might compromise scientific integrity, if there's concern about artifacts, about misinterpretation, about causing public alarm over something that turns out to be mundane. The agency can delay. They can take their time. They can ensure that when they do speak, what they say is bulletproof. The problem is, delay creates vacuum, and vacuum fills with speculation. Every day they stay silent. The conspiracies grow a little stronger. The questions get a little sharper. The trust erodes a little more. Real explanations for the delay exist. When you're dealing with faint, distant objects, data processing is complicated. Raw telescope images are noisy, filled with cosmic rays, scattered light, instrumental artifacts. You need to calibrate carefully, subtract backgrounds, register frames, stack properly. If you rush, you risk releasing images that look dramatic but are actually just noise amplified by poor processing. NASA learned this lesson before. In the early days of Hubble, rushed releases of uncalibrated images led to public relations disasters when the telescope's mirror flaw became apparent. Since then, the agency has been more cautious. Better to be slow and right than fast and wrong. That's the official reasoning, and it makes sense. Until you realise that Ray, with garage-level equipment and basic stacking software, produced images compelling enough to go viral. If he can do it in a weekend, why can't NASA do it in 2 weeks? Multi-wavelength confirmation is another factor. Professional astronomers don't just look at visible light. They want infrared data to measure temperature and dust emission. They want ultraviolet data to detect gas fluorescence. They want spectroscopy to identify specific molecules. They want radar returns if the object is close enough. Assembling all these observations, coordinating different telescopes, and synthesizing the results takes time. It's not laziness, it's rigor. You want the full picture before you make claims. You want to know if the bright points Ray captured show up in infrared, because if they do, they're emitting heat, which means they're real. If they don't, they're probably optical artifacts. That difference matters. It's the difference between a discovery and an embarrassment. So NASA waits. They collect. They analyze. And the public, watching the clock, grows impatient. Noise filtering is critical. Space telescopes like Hubble and JWST produce enormous amounts of data. Terabytes per observation session. Most of it is junk. Thermal noise, readout errors, stray photons. Automated pipelines filter it out, but those pipelines are conservative. They err on the side of removing anything that looks suspicious. If 3i/Atlas has faint structures that register as anomalous, the pipeline might classify them as artifacts and strip them from the final images. Scientists would then need to manually review the raw data, identify what was removed, and decide whether it's real. That process isn't quick. It involves comparing observations, running simulations, consulting experts. It's science at its most painstaking. But to the public, it looks like stonewalling. What are NASA's actual concerns? Avoiding another Oumuamua media frenzy has to be near the top. That object sparked debates that lasted years. Astrophysicists argued over whether its acceleration was caused by outgassing, light pressure, or something else entirely. The term light sail entered the conversation. A prominent astronomer seriously proposed it might be artificial. The media ran with it. Headlines screamed about alien probes. NASA spent months carefully walking back the speculation. Presenting data and models showing natural explanations was sufficient. It was exhausting. It distracted from other missions, and it set a precedent that interstellar objects trigger outsized reactions. If 3i/Atlas shows even a hint of strangeness, the agency knows what's coming. They'll be asked point blank if it's artificial. They'll face pressure to comment on escort hypotheses. Every statement will be scrutinized. Every image will be analyzed by thousands of armchair experts looking for proof of their preferred theory. It's a no-win situation. So they delay. They triple-check. They prepare their messaging. They try to control the narrative before it controls them. Public psychology plays a role too. Silence creates vacuum. Vacuum fills with fear and wonder and imagination. People project their hopes and anxieties onto the unknown. Some want 3i/Atlas to be something extraordinary. First contact, a probe from another civilization, proof we're not alone. Others want it to be mundane, just a comet, nothing to worry about. Both groups are watching NASA, looking for validation. And NASA, acutely aware of this dynamic, knows that whatever they say will satisfy some and enrage others. If they declare the anomalies are artifacts, the believers will accuse them of covering up the truth. If they admit the patterns are real but unexplained, the skeptics will demand immediate answers and criticize them for not having any. There's no clean exit, only damage control. Plausible internal debate probably goes something like this. One faction says release the data now, even if incomplete. Transparency builds trust. Show what you have, explain the uncertainties, and let the scientific community weigh in. Another faction argues for caution. Wait until you have definitive answers. Don't feed speculation. Don't give conspiracy theorists ammunition. Both positions are defensible. Both have historical precedent. And both are probably represented in conference rooms at Goddard and JPL, where scientists and administrators hash out strategy. The tension between scientific openness and institutional caution is real. It's not malicious, it's structural. But it looks suspicious from the outside. It looks like hiding something. Testing artifacts versus real structure is genuinely hard. You can't just look at an image and know. You need multiple observations from different angles, different instruments, different times. You need to model how artifacts propagate through processing pipelines. You need to simulate what the object should look like under various assumptions and compare those simulations to what you actually see. If the simulations match, great. If they don't, you dig deeper. You check for instrumental effects. You look for environmental factors like scattered moonlight or atmospheric turbulence. You rule out every mundane explanation before you even consider exotic ones. This is the scientific method at work, but it's slow, and when you're working with an object that's moving away from the sun, racing back into interstellar space, time is a luxury you don't really have. Every day it gets dimmer. Every week it gets harder to observe. The clock is ticking. And NASA knows it. Are they seeing the same 5-point pattern? That's the question everyone wants answered. If Hubble or JWST captured images showing smooth, asymmetric coma structure with no bright nodes, the mystery collapses. Rays footage becomes a cautionary tale about amateur processing. But if their images show the same pattern, or worse, show it more clearly, then the game changes. Then the discussion shifts from is it real to what is it? And that's a much harder conversation. Because once you confirm the pattern exists, you have to explain it. And the explanations, as we've explored, require increasingly specific conditions, increasingly unlikely coincidences, until you reach a point where natural explanations start sounding as contrived as artificial ones. That's the nightmare scenario for NASA. Not that 3i/Atlas is artificial, but that they can't definitively prove it isn't. Speculation grows in that silence. Not just fringe theories. Serious people asking serious questions. Astronomers at universities forming their own observing campaigns. Data scientists requesting access to public archives to analyse for themselves. Journalists digging, making calls, trying to find someone who'll talk off the record. The pressure builds, and eventually it'll reach a threshold. Eventually NASA will have to say something. The briefing will happen, the data will be released, and we'll find out whether the escort hypothesis has any basis in reality, or whether Ray captured a perfect storm of artifacts that fooled everyone. Either way, the tension breaks. But until then, we're left hanging. Left wondering. Left staring at 5 bright points in an amateur image and asking ourselves the question that defines our relationship with the cosmos. Are we looking at nature at its most strange, or intelligence at its most subtle? And which answer would be more unsettling? Next, we dive deeper. We explore the escort hypothesis properly. If those points were real, if something actually accompanied 3i/Atlas on its journey through our solar system, what configurations would fit the data? What physical arrangements could produce what Ray observed? It's a thought experiment, a what-if scenario. But thought experiments have a way of revealing possibilities we hadn't considered, and sometimes those possibilities turn out to be true. Part 6. The escort hypothesis. If it were real, what configuration fits the data? Let's play a game. Let's assume, just for the next 1,000 words, that Ray captured something real. That the 5 bright points aren't artifacts or illusions or misinterpreted dust jets. that they're actual discrete objects or structures, maintaining position relative to the comet's nucleus as it spins and travels through space. It's a big assumption, maybe a wrong one, but assumptions are tools for exploration. They let us map possibility space. They let us ask, if this were true, what would it look like? What physics would it require? What configurations make sense? And crucially, what observations would prove or disprove it? So let's explore the escort hypothesis not as believers, but as investigators. Let's see where the idea leads and whether it holds up under scrutiny. First, the geological possibilities. Comets can fragment. Tidal forces, thermal stress, rotational breakup, all of these can split a nucleus into multiple pieces. If 3I/ATLAS fractured at some point in its past, those fragments might still be travelling together, held in loose gravitational embrace. From a distance, you'd see multiple bright points, each fragment reflecting sunlight, each contributing to the overall coma. The spacing would depend on when the breakup occurred and what forces were acting. But here's the problem. Gravitational interactions between fragments would cause orbital evolution. The pieces would drift apart or collide. Maintaining 5 fragments in a stable ring configuration for the months or years it took 3I/ATLAS to reach our solar system requires precise initial conditions. Possible, but statistically unlikely. And fragments orbiting a central body would show periodic brightness variations as they eclipsed each other or changed phase. We don't see that. The 5 points maintain relatively constant brightness. That's a strike against the fragment hypothesis. What about symmetric vent positions? Imagine a nucleus with 5 active regions spaced evenly around its equator. As the comet approaches the Sun, these vents heat up and start ejecting material. Each vent produces a bright plume of dust and gas. From our viewing angle, those plumes appear as discrete points surrounding the nucleus. This is a natural explanation. It doesn't require anything exotic, but it does require the nucleus to have a very specific shape and structure. The vents need to be at approximately 72-degree intervals. They need to activate simultaneously or in quick enough succession that they all appear active in a single image. And the dust they eject needs to scatter light efficiently in our direction. That's a lot of requirements. Not impossible, but narrow. And the question remains, how did the nucleus acquire such symmetric vent positions? Random accretion over billions of years doesn't produce regular patterns. Collisions create chaos, not order. So if the vents are real, something shaped the nucleus in a deliberate way. Even if that shaping was purely geological, the result looks designed. Crystalline or lattice-like internal structure offers another angle. Some minerals form in repeating patterns. If the comet's interior has crystalline regions arranged in a geometric lattice, thermal stress could fracture along those planes, creating symmetric vent positions. It's analogous to how crystals cleave along specific axes when struck. The internal order of the crystal dictates the external shape of the fragments. Applied to a comet, internal crystalline structure could guide where volatiles escape, producing regular jet patterns. This is plausible on small scales. Ice crystals, for instance, are hexagonal, but extending this to a comet-sized body requires the entire nucleus to have long-range order, and cometary nuclei are thought to be loosely bound aggregates, rubble piles of ice and rock, not single crystals. Still, if 3I/ATLAS formed in unusual conditions, maybe in an environment with strong magnetic fields or under slow, controlled accretion, unusual internal structure isn't impossible, just very unexpected. Plasma-oriented explanations venture into more speculative territory. Plasmas can form structures. Magnetic fields can trap charged particles in stable configurations. In laboratory settings, researchers have created plasma knots, toroidal shapes, structures that persist far longer than you'd expect from random ionized gas. Could something similar happen in a comet's coma? If the comet is ejecting ionized material, and if there's a magnetic field present, either from the comet itself or from interactions with the solar wind, plasma could organize into discrete nodes. These nodes would glow as ions recombine or as electrons emit photons. They'd appear bright. And if the magnetic field geometry were just right, they could arrange in symmetric patterns. The challenge is that comets aren't strongly magnetic. Their nuclei are icy rock, not magnetized iron. The solar wind provides some ambient field, but it's weak at the distances we're discussing. Creating stable plasma structures would require conditions far from what we normally associate with comets. So while this isn't ruled out, it's exotic. It requires physics at the edge of what we understand about cometary environments. Photonic resonance is even more speculative. Light can create force. Radiation pressure is real and measurable. Photons carry momentum. When they reflect off or are absorbed by particles, they push. In principle, if dust particles in the coma were the right size and composition, they could form stable patterns where radiation pressure balances gravitational attraction. These would be photonic resonance points, places where light from the sun creates standing waves in the dust distribution. The pattern would be geometry dependent, possibly producing symmetric arrangements. This has been proposed theoretically for other astrophysical systems, but never confirmed observationally. Applying it to 3I/ATLAS requires the dust to have very specific properties, and the sun's radiation to interact with the coma in ways that seem fine-tuned. It's not impossible, it's just unlikely, and it raises the question, if such resonances exist, why haven't we seen them in other comets? Astrodynamics gives us more tangible options. Small fragments orbiting the comet after a prior breakup could create the pattern Ray observed. If the comet split violently at some point, ejecting material at specific velocities, some of that material could enter orbit around the remaining nucleus. Orbital mechanics would then govern their motion. Depending on the mass distribution and rotation of the nucleus, stable orbits could exist. The fragments would circle, maintaining relatively fixed positions in the rotating frame of reference. This is real physics. Moons orbit planets. Rings orbit gas giants. The same principles apply at smaller scales. But comet nuclei are tiny. Their gravity is weak. Keeping 5 fragments in stable orbit would require them to be very close, practically skimming the surface. And at those distances, atmospheric drag from the coma would cause orbital decay. The fragments would spiral inward and crash. The configuration wouldn't last. Unless the fragments are continuously replenished somehow, or unless the coma is much less dense than expected, orbital mechanics struggles to explain prolonged stability. Part 7. Reconstructing the 3D motion. From amateur data, you're looking at a spinning comet millions of miles away through a telescope that wobbles slightly with every passing breeze. You take dozens of exposures, stack them together, sharpen the result, and suddenly you see something that wasn't obvious before. 5 bright points, arranged in a ring, moving in ways that seem coordinated. The question everyone wants answered is simple. Are those points rotating with the comet, or are they moving around it? Ray's images don't give us the luxury of a Hollywood 360 fly-around. We're stuck with a 2-dimensional projection of a 3-dimensional object doing something complicated in the darkness between stars. But scientists have tricks for extracting motion from flat images, and some of those tricks work even with amateur data. The first technique involves differential luminosity analysis. Sounds fancy, but the concept is straightforward. If you compare the brightness of each point across multiple frames, you can start to map how they're changing position relative to the core. If all 5 points get brighter and dimmer together, they're probably locked to the nucleus, rotating with it as jets or vents activate and deactivate based on sunlight angle. But if they brighten independently, in sequence, like Christmas lights going around a tree, then you might be looking at separate objects orbiting the comet. Ray's frames show something in between. The points don't all pulse together, but they don't follow a clean sequential pattern either. It's messier than that, more organic. Which could mean the rotation axis is tilted relative to our viewing angle, creating a complex pattern of illumination as different features rotate in and out of view. Then there's coma backscatter analysis. The dust cloud surrounding 3I/ATLAS isn't just decoration, it's a diagnostic tool. When sunlight hits dust particles, some of that light bounces back toward Earth. By analysing which parts of the coma are brightest, researchers can infer the orientation of the nucleus. If the dust is being thrown off a spinning body, the backscatter pattern will shift in predictable ways as different hemispheres face the sun. Ray's images show subtle shifts in coma brightness that suggest the object is indeed rotating. But the period seems short, too short for a typical comet nucleus. Most comets rotate over several hours, some take days. But the changes Ray captured happened over just 60 to 90 seconds. That implies either very rapid rotation, which would be unusual for an object large enough to hold a coma together, or precession, a wobbling motion like a spinning top that's starting to fall over. Precession can create illusions. A slowly rotating object that's also precessing can appear to change orientation much faster than it actually is. This happens because you're seeing the combined effect of two rotations happening at different rates. It's the same reason a wobbling football looks like it's spinning faster than it really is. But here's where things get weird. If the 5 points are fixed to the nucleus, locked into positions on the surface like vents or craters, then as the object rotates, we should see them move in predictable arcs. They should spread out, overlap, change their relative positions dramatically. Instead, they maintain their spacing. They stay in formation. That persistence is what keeps the escort hypothesis alive. Some researchers have suggested the points might not be on the surface at all. They could be dust clumps trapped in stable orbits around the nucleus, held in place by the object's weak gravity and the pressure of outgassing jets. This phenomenon, called a trochoidal path, happens when particles get caught in repeating loops, spiralling around but never escaping or falling back. The math works. Small particles in certain size ranges can be suspended in quasi-stable orbits around active comets. They'd appear as bright points because they're reflecting sunlight, while the darker nucleus behind them stays dim. And if the comet is rotating, those particles might maintain their relative positions if they're orbiting faster than the nucleus spins. But there's a problem. For 5 separate dust clumps to arrange themselves in a symmetric ring and stay there requires either extraordinary coincidence or some kind of organizing force. Gravity alone doesn't explain symmetric spacing. You'd need something else. Maybe electric fields in the coma, maybe magnetic structures if the nucleus has any residual magnetism, maybe nothing at all, and the symmetry is just an artifact of how Ray processed his images. Scientists who study comet rotation professionally, like those who analyse 67P during the Rosetta mission, know how complicated spin states can be. 67P tumbled chaotically, its rotation axis wandering over time due to asymmetric outgassing. Jets firing from one side created torque, like tiny rocket engines nudging the nucleus into new orientations. If 3I ATLAS is doing something similar, its rotation could be changing even as we watch. Ray's data can't definitively answer whether the 5 points are surface features, orbiting fragments, or optical illusions. The resolution isn't high enough, the time coverage isn't long enough, but the data does suggest complexity. It hints at something more structured than a simple spinning rock, and that's what makes this so tantalizing. Because if you assume, just for a moment, that the 5 points are real objects in orbit, you can calculate what their orbital period would need to be. Based on the shifts between Ray's frames, if those points were circling the nucleus, they'd complete one orbit roughly every 3 to 5 minutes. That's insanely fast. At that speed, they'd need to be very close to the nucleus, just a few dozen meters out, or the centrifugal force would fling them into space. Could fragments orbit a comet nucleus that quickly? Maybe if the object is dense enough and the fragments are small enough, but it's right at the edge of plausibility, which means we're either looking at an extremely unusual natural configuration, or we're seeing something else entirely. And until someone points a much better telescope at 3I ATLAS and tracks these points over hours instead of minutes, we won't know which it is. But the fact that amateur data got us this close to an answer, that's worth remembering. Part 8. Historical Precedents. When amateurs beat the professionals. Professional astronomy is a machine. Telescopes the size of buildings. Computers running calibration algorithms refined over decades. Teams of scientists who've spent entire careers learning how to extract signal from noise. You'd think nothing gets past that kind of firepower, but history says otherwise. March 1995. A comet named Hale-Bopp is cruising through the outer solar system, still more than a year from its closest approach to the Sun. Professional observatories are monitoring it, sure, but their images go through processing pipelines designed to remove anything that looks weird. Cosmic rays, hot pixels, tracking errors, anything that doesn't fit the expected profile of a smooth, symmetric coma gets filtered out as noise. Then an amateur astronomer in Texas notices something strange in his backyard images. The comet's nucleus appears doubled, like there are 2 bright cores instead of 1. He posts his images online, and within days other amateurs confirm it. Hale-Bopp has fragmented. There's a smaller piece trailing the main nucleus. The professionals check their archived data. Sure enough, the fragment is there, but their automated pipelines had flagged it as an artifact and removed it. The amateurs saw it first because they didn't trust the algorithms. They looked at the raw data with human eyes and notice something that shouldn't be there. Or consider July 1994. Comet Shoemaker-Levy 9 is about to slam into Jupiter in what will become one of the most watched astronomical events in history. Professional observatories have the impact sites calculated down to the minute. But amateur imagers around the world are capturing something the big scopes miss. Faint fragments trailing the main chain. Pieces too dim for the automated surveys but visible to patient observers, willing to stack dozens of exposures by hand. Those fragments turned out to be real. Some of them hit Jupiter hours after the main impacts, creating secondary fireballs that nobody had predicted. Then there's Comet 17P Holmes, October 2007. This normally faint comet suddenly explodes in brightness, becoming visible to the naked eye overnight. Amateur astronomers are the first to capture detailed images of the expanding debris cloud. They see structures in the outburst, radial jets and spiral patterns that suggest the nucleus is rotating and throwing off material in organised streams. By the time professional observatories swing their instruments toward Holmes, the initial outburst has already evolved. The amateurs captured the early phase, the moment of maximum chaos, because they were already looking. The professionals had to scramble to catch up. Why does this keep happening? How do backyard observers with consumer-grade equipment beat billion-dollar facilities to the punch? Part of it is coverage. There are thousands of amateur astronomers scattered across the globe, observing every clear night. They're not limited by telescope allocation committees or grant funding. If something interesting appears, they point their scopes at it immediately. No proposals, no peer review, just pure curiosity driving them to capture whatever photons they can. But there's another factor. Professionals use standardized processing techniques designed to produce clean, publishable images. Those techniques involve aggressive noise reduction, flat field correction, and artifact removal. Anything that doesn't look like a smooth cosmic object gets filtered out. This is usually the right approach. Most of the weird stuff in astronomical images really is noise, but not always. Amateurs, especially those who process their own images, often skip the aggressive filtering. They use gentler stacking methods. They experiment with different sharpening kernels. They're not trying to produce data for a journal article. They're trying to see what's actually there, noise and all. And sometimes, buried in that noise, is something real. Ray's images of 3i Atlas fit this pattern perfectly. His stacking choices were unconventional. He used tight crops and moderate sharpening instead of the heavy-handed noise reduction that professionals would apply. That's why the 5 points are visible in his images. A standard pipeline might have smoothed them away as artifacts. Does that mean they're real? Not necessarily. It means they're persistent enough to survive his processing, which is interesting but not conclusive. The danger with amateur discoveries is that they can also introduce artifacts that look compelling, but aren't actually there. Rolling shutter effects, tracking errors, sensor blooming, hot pixels that happen to line up across multiple frames. All of these can create false structures that seem too organized to be random. Professional processing removes these artifacts specifically to avoid false discoveries. So we're left with a tension. Amateurs see things professionals miss, but they also see things that aren't really there. The key is distinguishing between the two, and that requires careful analysis, independent verification, and patience. In Ray's case, the verification is coming. Other amateur astronomers are now pointing their telescopes at 3i Atlas, trying to reproduce his results. Some are seeing the 5 points, others aren't. Some claim they see 6 points, or 4, or a continuous ring. The variance suggests processing choices matter enormously. But even if the 5-point formation turns out to be an artifact, Ray's images have already accomplished something valuable. They've forced the professional community to look more carefully at 3i Atlas, to check their own data for structures they might have filtered out, to consider the possibility that this interstellar visitor is more complex than the initial observation suggested. And that's the real legacy of amateur astronomy. Not that it replaces professional work, but that it asks different questions. It looks at the data through fresh eyes, unencumbered by assumptions about what should or shouldn't be there. Sometimes those fresh eyes see artifacts, but sometimes, just sometimes, they see the truth before anyone else does. And until NASA releases its own images of 3i Atlas, until we see what Hubble or James Webb or ground-based professional observatories have captured, Ray's footage remains the most detailed publicly available view of this object, which means, for now, the amateurs are leading the way, and the world is watching to see if they've found something extraordinary. or just revealed how easy it is to be fooled by patterns in the dark. Part 9. The conspiracy channels are wrong, but not entirely. Let's talk about the people who are absolutely convinced that Ray's images show alien spacecraft. They're wrong, almost certainly. But if you dismiss them entirely, you miss something important about why the 5-point formation is actually strange, even if it's not evidence of extraterrestrial technology. The conspiracy videos started appearing within hours of Ray's images going viral. Dramatic music, urgent narration, red circles drawn around the 5 points with labels like escort craft and scout probe, claims that NASA is covering up evidence of intelligent monitoring, comparisons to every UFO sighting in the past 50 years, the usual playbook. Most of what they're showing is nonsense. Lens flares mistaken for structured objects, sharpening halos around bright stars interpreted as force fields, colour gradients from sensor noise rebranded as propulsion signatures. If you don't understand how digital cameras work, how stacking algorithms process data, how optical artifacts propagate through image enhancement, then Ray's footage can look like almost anything you want it to be. But here's the thing. If you strip away the dramatic music and the conspiracy framework, some of their observations aren't entirely baseless. They're noticing real features in the images that don't have straightforward explanations. The even spacing of the 5 points bothers optical physicists, not just conspiracy theorists. Diffraction patterns can create bright spots around celestial objects, but they typically appear as spikes or asymmetric blooms, not evenly distributed points arranged in a ring. Dust jets from a rotating comet can create multiple bright regions in the coma, but synchronized timing across 5 equidistant locations requires either precise geometric alignment of surface vents or something else organizing the pattern. Then there's the flicker synchronization. Several independent observers who've processed Ray's frames report that the 5 points seem to brighten and dim together, not randomly. This coordinated luminosity variance is exactly the kind of detail conspiracy channels jump on as evidence of artificial control. But it's also the kind of detail that suggests a real physical process is happening, even if that process is entirely natural. One possible explanation involves rotating dust structures. If the comet nucleus has a specific shape, maybe elongated or flattened, and it's rotating quickly, dust thrown off the surface could form temporary shells, or rings that persist for minutes before dispersing. As the nucleus rotates, these shells might catch sunlight at repeating intervals, creating the appearance of synchronized flashing. It's speculative, but it's physics, not science fiction. Another explanation involves electric fields in the coma. Comets travelling through the solar wind accumulate charge. That charge can organize dust particles into patterns, pulling them into filaments or concentrating them at specific distances from the nucleus. Lab experiments have shown that charged dust can self-organize into surprisingly regular structures. If 3I ATLAS is electrically active, which interstellar objects might be due to their high relative velocity through space, those electric fields could create the geometric patterns Ray's images seem to show. The conspiracy channels don't mention electric fields or trochoidal dust orbits. They skip straight to extraterrestrial surveillance. But the underlying observation, that the pattern looks organized, isn't crazy. It's a reasonable response to data that genuinely appears structured. Where the conspiracy theorists go wrong is in assuming that structure implies intelligence. Humans are pattern recognition machines. We see faces in clouds, pyramids on Mars, messages in white noise. Our brains evolved to detect agency, to assume that organized patterns means someone organized them. This instinct kept our ancestors alive when rustling grass might mean a predator, but it leads us astray when analyzing cosmic phenomena. The universe produces symmetry all the time without any intelligence involved. Snowflakes are hexagonal because of the molecular structure of ice, not because tiny architects are designing them. Saturn's rings are layered and banded because of orbital resonances, not because someone arranged them that way. Spiral galaxies form their elegant arms through gravitational physics, not intentional engineering. But symmetry is compelling. When we see it, especially in unexpected contexts, our first instinct is to ask who made it. And if the symmetry appears in images of an interstellar object, an object that came from outside our solar system and might carry artifacts or information from other civilizations, well, that instinct goes into overdrive. So the conspiracy channels are wrong about aliens. but they're not wrong about the strangeness. The 5-point formation, if it's real and not just an artifact of processing, represents something that doesn't fit easily into existing comet models. That's worth investigating. That's worth taking seriously. The problem is that taking it seriously means doing the boring work, running simulations, testing alternative hypotheses, comparing the data to known cometary behaviour, waiting for better observations. Conspiracy theorists don't have the patience for that. They want the answer now, and they want it to be dramatic. Scientists, meanwhile, are comfortable with uncertainty. They know that most anomalies turn out to have mundane explanations. They've seen too many impossible observations collapse under scrutiny. So they approach Ray's images with caution, looking for the simplest explanation first before considering exotic alternatives. That caution is appropriate, but it can also lead to premature dismissal. If the 5 points are immediately categorized as artifacts without careful analysis, we might miss a genuine discovery about how interstellar objects behave. We might overlook a real process that could teach us something new about dust dynamics, rotation states, or the structures that form in active coma. The truth, as usual, is probably somewhere in the middle. The 5 points are likely a combination of real features and processing artifacts. Some of what Ray captured is probably genuine jets or dust concentrations that exist in the actual coma, and some of it is probably enhancement, bright spots amplified by stacking and sharpening until they look more defined than they really are. Separating those two components requires better data, until NASA releases professional observations, until multiple independent teams analyse 3i ATLAS with calibrated instruments. We won't know for certain what's real and what's illusion. But the conspiracy channels have done one useful thing. They've kept attention focused on the anomaly. They've made sure that when NASA does release its data, millions of people will be watching, and if there's anything unusual in those images, anything that resembles the patterns Ray captured, the pressure will be on scientists to explain it. So yeah, the conspiracy theorists are wrong, but they're asking the right question. What's actually out there, and why does it look like that? Even if the answer turns out to be boring, the question is worth asking. Because every now and then, just often enough to keep us humble, the universe surprises us with something that shouldn't exist. And we won't know if 3i ATLAS is one of those surprises until someone looks at it properly. Part 10. Cross-object comparison. Atlas versus Oumuamua versus Borisov. 3 interstellar visitors have entered our solar system in the past 8 years. 3 objects that originated somewhere else, formed around a different star, travelled through the void between stellar systems for potentially millions of years before our sun's gravity caught them and bent their trajectories through our neighbourhood. Each one has been strange in its own way, and if you line them up, a pattern starts to emerge. Not a pattern that proves anything, but a pattern that makes you wonder if we've been thinking about interstellar space the wrong way. October 2017. 1. Oumuamua is spotted streaking through the inner solar system, already past its closest approach to the Sun, and heading back out toward interstellar space. The name means scout, or messenger in Hawaiian, and it's the first confirmed interstellar object ever detected passing through our system. Almost immediately it's weird. The orbit is wrong. Oumuamua is accelerating slightly as it moves away from the Sun, more than gravity alone can explain, not by much. Just a tiny excess velocity that shows up in the tracking data, but it's there, and it shouldn't be. Comets accelerate due to outgassing, jets of vaporized ice pushing them like tiny rocket engines. But Oumuamua shows no visible coma, no tail, no evidence of activity. It's too small and moving too fast for detailed imaging, but spectra reveal a dark reddish surface, more like an asteroid than an active comet. So what's pushing it? Theories multiply. Maybe it's outgassing something exotic, a volatile that doesn't produce a visible coma. Frozen nitrogen, frozen hydrogen. Materials we wouldn't expect in our solar system, but that might be common wherever Oumuamua came from. Or maybe it's shaped strangely, elongated like a cigar or flattened like a pancake, and radiation pressure from sunlight is pushing it more efficiently than a typical space rock. One Harvard astronomer suggests it could be artificial, a light sail, a probe, technology built by another civilization and sent drifting through the galaxy. The paper is published in a respected journal, and the media goes wild. Most scientists reject the artificial hypothesis, not because it's impossible, but because the evidence doesn't require it. Oumuamua can be explained with natural processes if you make reasonable assumptions about its composition and shape. Jumping to aliens is premature, but the fact that a respected scientist even published the idea tells you how strange Oumuamua was. It forced astronomers to consider possibilities they'd normally dismiss out of hand. August 2019. 2. I Borisov appears, and it's the opposite of Oumuamua in almost every way. It has a bright, obvious coma, a long, beautiful tail. Spectra show familiar cometary molecules, carbon monoxide and water vapour, exactly what you'd expect from an icy body heated by the sun. Borisov looks normal, acts normal. If you didn't know it came from another star system, you'd think it was just another comet from our own Oort cloud. The relief among astronomers is palpable. See, interstellar objects aren't that weird. They're just comets and asteroids that happen to wander in from somewhere else. But Borisov has its own quirks. Its carbon monoxide concentration is extremely high, higher than typical comets from our system. Its dust production rate varies chaotically, spiking and dropping without obvious pattern, and its nucleus appears to be fragmenting, shedding pieces as it rounds the sun, behaviour that suggests it's structurally weak, held together by ice that's now sublimating rapidly. Still, Borisov is understandable. It fits within the range of behaviours we've seen from solar system comets. It's exotic, sure, but not alien. Not in the sense that makes people nervous. Now we have. 3I ATLAS, and it's splitting the difference between its two predecessors in the strangest way possible. Like Oumuamua, ATLAS shows features that don't fit standard models. The 5-point formation, the rapid rotation or precession, the shifting structures in the coma that Ray's images seem to capture. But unlike Oumuamua, ATLAS is clearly active. It has a visible coma. It's throwing off dust and probably gas. It's behaving like a comet should, optically speaking. Yet like Borisov, ATLAS seems to be fragmenting or undergoing structural changes. The dark ridges in the coma, the possible shadowing effects, the way the bright core shifts position between frames. These suggest something is happening to the nucleus, some process that's altering its shape or surface properties in real time. But neither Oumuamua nor Borisov showed symmetric patterns like the 5 points. Neither one produced imagery that made people immediately think formation or escort. That's new. That's unique to ATLAS. So what does it mean? One possibility is that we're just seeing more diversity as our sample size grows. 3 objects is still a tiny number, statistically meaningless. If we wait another decade and detect 30 interstellar visitors, we might find that each one is weird in its own way, and the weirdness averages out to a full spectrum of natural phenomena. Elongated asteroids, fragmenting comets, objects with unusual rotation states, all of it natural, all of it explained by the chaotic processes that form and eject material from other star systems. Another possibility is selection bias. We only notice interstellar objects that are unusual. Oumuamua was spotted because it was moving fast on a strange trajectory, Borisov because it had an obvious tail, ATLAS because of its brightness and activity. Hundreds of boring interstellar rocks might pass through our system every year, dark and silent, and we'd never know. We're building a catalogue of the weird ones because those are the only ones we can see. But there's a third possibility that's harder to dismiss. Maybe interstellar objects really are more varied than solar system objects because they come from more varied environments. Our solar system formed from a single molecular cloud around a single star. Everything here shares a common origin. Same initial composition. Same formation, temperature and pressure. Same bombardment history during the early chaotic period. Interstellar objects come from everywhere. Different stars, different nebulae, different epochs in galactic history. An object that formed around a hot blue giant would have a completely different thermal history than one that formed around a cool red dwarf. An object ejected from a system during a close stellar encounter might have a different structure than one that drifted away slowly over millions of years. If that's true, if interstellar space is full of objects shaped by wildly different processes, then we should expect every visitor to surprise us. Not because they're artificial or anomalous, but because they're showing us what happens in environments we've never sampled. 3I ATLAS might have formed in a system with extreme tidal forces, creating internal structures or layering that produces symmetric outgassing patterns. Or it might come from a debris disk around a binary star tumbling chaotically for eons until its rotation state locked into a complex precession. Or it could be a fragment from a larger body that's shattered in a collision, and we're seeing the geometric remnants of that fracture. All of these are natural explanations. None require intelligence or technology, but all of them push the boundaries of what we thought interstellar objects could look like. And that's the real significance of comparing ATLAS to its predecessors. We're not just cataloguing weird rocks, we're starting to map the diversity of planetary materials across the galaxy. Every interstellar visitor is a free sample from a star system we'll never reach, a messenger carrying information about conditions light years away. Oumuamua taught us that some objects accelerate mysteriously. Borisov taught us that some have extreme compositions, and ATLAS, if the 5-point formation holds up, might teach us that some have geometric structures we haven't seen before. Or it might teach us nothing, except how easy it is to misinterpret amateur images of distant objects. But we won't know until we look, until NASA points its best instruments at 3i ATLAS and shows us what's really there, hidden behind the blur and noise of Ray's backyard telescope. And whatever that reveals, it'll be one more data point, one more piece of the puzzle, 3 visitors down, thousands more to come if we keep watching the sky. Part 11, November 2025. The strange quasi-repeating solar radio burst. While everyone's focused on 3i ATLAS, something strange is happening much closer to home. Something that might explain why we're seeing patterns where we shouldn't, or might just prove that the universe loves messing with us. November 6th, 2025. The Deep Space Network picks up an unusual radio burst from the Sun. Not unusual because it's loud. Solar radio emissions happen all the time. The Sun is a giant ball of plasma with magnetic fields twisting and snapping constantly, and every time a field line breaks and reconnects, it accelerates particles that emit radio waves. Type 3 bursts, Type 2 bursts. Solar astronomers have classified them into neat categories based on frequency and duration. But this burst doesn't fit the categories cleanly. It starts as a typical Type 3 event, fast-drifting high-frequency emission consistent with electron beams travelling outward through the corona. But then it pauses. The frequency stabilises instead of drifting lower, and over the next 17 minutes it pulses, not randomly, not chaotically, in a pattern that almost resolves into regular intervals. The data shows peaks at roughly 3.2-minute intervals, then the pattern shifts, 4.1 minutes, then back to 3-point-something. The periodicity is there, but it's slippery, like trying to catch a rhythm that keeps changing tempo. Heliophysicists are divided. Some argue it's just multiple overlapping bursts, coincidental timing making it look like a pattern. Solar activity is messy. Dozens of processes happen simultaneously. If you stare at the noise long enough, you'll see rhythms that aren't really there. Others point out that 3 to 4 minute periodicities are real features of solar oscillations. The Sun rings like a bell, vibrating at specific frequencies determined by its internal structure. Those oscillations can modulate radio emissions, creating quasi-periodic patterns in the data. Not perfectly regular, because the Sun is turbulent, but consistent enough to show up in careful analysis. But what bothers people is the timing. This burst happens while 3i ATLAS is making its closest approach to the Sun. While amateur astronomers around the world are pointing their telescopes at the comet, capturing images that might show geometric patterns. While NASA is preparing to release its official observations, correlation doesn't imply causation. The Sun doesn't care about comets. Solar radio bursts don't respond to icy rocks millions of kilometers away. The timing is coincidence. Probably. But here's why it matters for the ATLAS mystery. Solar radio emissions can interfere with observations, not directly, not by blocking light or scrambling telescopes, but indirectly, by affecting the space environment around comets. The solar wind carries magnetic fields and charged particles. When those fields fluctuate, when the particle density spikes, comets react. Their comas compress. Dust tails shift. Jets activate or shut down in response to changing pressure. If the solar radio burst coincides with unusual solar wind conditions, then 3i ATLAS might be responding to those conditions. The 5-point pattern Ray captured might be the result of the comet's coma reacting to pressure waves in the solar wind. Dust concentrating at specific distances where incoming and outgoing flows balance. Plasma structures forming at magnetic field boundaries. This has been observed before. Comet Eson in 2013 showed strange coma structures as it approached the Sun, bright knots and filaments that appeared and disappeared over hours. Analysis later revealed those structures correlated with solar wind disturbances. The comet was being buffeted by space weather, and its coma was showing the effects. Could the same thing be happening with Atlas? Could the 5 points be solar wind artifacts, temporary structures that only exist because the sun is doing something unusual right now? It's possible, but it doesn't fully explain the symmetry. Solar wind interactions with comets are typically asymmetric, creating tails that point away from the sun and bow shocks on the sunward side. Getting 5 evenly spaced bright points requires either a very specific alignment of magnetic structures, or again, something about the comet itself that organises the response symmetrically. And then there's the periodicity problem. If the solar radio burst is pulsing every 3 to 4 minutes, and the 5 points in Ray's images seem to flicker or shift on similar timescales, is that coincidence? Or is there a physical connection? Solar rotation takes about 27 days at the equator. Coronal structures rotate with the sun, sweeping past Earth like lighthouse beams. But 3 to 4 minute periods are far too fast for that. They imply either localized oscillations, small regions of the corona vibrating independently, or rotation of structures much smaller than the sun itself. The most likely explanation involves magnetic loops. The sun's corona is full of them, arches of hot plasma trapped along magnetic field lines. These loops can oscillate, bouncing like plucked strings, at periods ranging from seconds to minutes depending on their size and temperature. If one of these loops is oscillating at the right frequency, and if it's pointed toward Earth, we'd see the radio emission pulse in time with the oscillation. But why would such an oscillation affect a comet millions of kilometers away? The radio waves themselves don't carry enough energy to influence dust or plasma. They're just electromagnetic radiation, passing through space without interacting with anything unless there's a receiver tuned to the right frequency. Unless the radio burst is a symptom, not a cause, a visible signature of deeper solar wind disturbances that are affecting both the sun's corona and 3I Atlas simultaneously. In that case, the periodicity would be a clue to the underlying process. Something in the solar wind is oscillating, creating pressure waves that ripple outward, and both the sun's radio emission and the comet's coma are responding to the same driving force. Scientists are now combing through solar wind data from spacecraft like Parker Solar Probe and Solar Orbiter, looking for correlations. Preliminary results show elevated magnetic field variability during the period when Ray captured his images. Nothing extreme, no major flares or coronal mass ejections, just increased turbulence, small-scale fluctuations that wouldn't normally be noteworthy. But in the context of 3I Atlas, those fluctuations might matter. They might be the missing piece that explains why the 5 points appeared when they did, why Ray's timing was perfect, even if he didn't know it, or the solar activity might be irrelevant, a red herring, the universe throwing noise into the data at exactly the wrong time, making it harder to separate real comet features from environmental effects. This is the frustration of astronomy. You can't control the experiment. You can't turn off the sun's magnetic field to see what the comet does without it. You observe what's there when it's there, and try to untangle cause from correlation after the fact. But here's the unsettling thought. If the sun can produce quasi-periodic radio bursts that look almost organized, almost regular, then the universe is capable of creating misleading patterns, not just in images of distant comets, but in data we consider objective. Frequency spectra, light curves, time series measurements. We trust instruments more than we trust our eyes. We know our brains see patterns in static, but instruments see patterns too sometimes, when the signal and the noise interact in just the right way. And sorting out which patterns mean something from which patterns are accidents of timing requires more than good data. It requires context, history, comparison to other events. Right now, 3I Atlas is giving us a pattern we don't understand, during a period when the sun is also giving us a pattern we don't fully understand. Maybe they're connected, maybe they're not. But until someone figures it out, the possibility hangs there. Are we looking at a comet doing something genuinely strange? Or are we looking at a comet doing normal things while the sun adds confusion to the background? And if it's the latter, how many other cosmic mysteries are just the result of bad timing, interesting objects observed during noisy moments, producing data that looks significant but isn't? That's the question keeping solar physicists up at night right now. And the answer might matter far beyond 3I Atlas. Part 12. Breakthrough in quantum gravimetry. You can't see gravity. You can feel it, sure, when you trip and fall or watch an apple drop from a tree. But you can't point a telescope at an object and measure its gravitational field directly. Gravity isn't light. It doesn't emit photons. It's just the curvature of space-time, invisible and silent. Except now we can measure it. Sort of. May 2025. A research team at the National Institute of Standards and Technology announces a breakthrough in quantum gravimetry. They've built a portable device, roughly the size of a refrigerator, that can detect changes in gravitational field strength with unprecedented precision. We're talking sub-millimeter resolution, the ability to measure tiny variations in gravity caused by objects smaller than a grain of sand. The technology isn't new in concept. Atom interferometry has been around for decades. The basic idea is elegant. You take a cloud of ultra-cold atoms, split them into two paths using laser pulses, let them travel through slightly different gravitational environments, then bring them back together and watch how they interfere. The interference pattern tells you about the gravitational field difference between the two paths. What's new is the precision. Previous atom interferometers could detect gravity, variations, sure, but they needed hours of integration time and carefully controlled environments. This new device works in minutes, in field conditions, with accuracy that approaches theoretical limits. Why does this matter for astronomy? Because gravitational field mapping could revolutionize how we study small bodies in space. Right now, when we want to know the mass distribution of an asteroid or comet, we have to send a spacecraft close enough to measure how its trajectory bends. That's how we learned that Comet 67P has a weird density distribution, lighter than expected in some regions, suggesting internal voids or cavities. But it required the Rosetta mission, years of planning and billions of dollars to get that data. Imagine instead pointing a quantum gravimeter at 3I ATLAS and measuring its gravitational signature from Earth. You couldn't map the whole object, not from this distance, but you could detect asymmetries, mass concentrations, dense regions that pull harder than surrounding areas. If the 5-point formation is real, if there really are distinct objects orbiting the nucleus, a sensitive enough gravimeter should see them. Each object would have its own gravitational signature, tiny perturbations in the field that shift as they orbit. The pattern would be unmistakable. Of course, there's a problem. 3I ATLAS is millions of kilometers away. Its total mass is maybe a few billion tons, which sounds like a lot until you realize that's nothing compared to Earth's nearly 6 sextillion tons. The gravitational pull from Atlas at this distance is vanishingly small, completely swamped by local gravity from the Moon, the Sun, even passing trucks on the highway near the detector. But the researchers claim they're working on it. The next generation device, planned for deployment in 2027, will operate in space, aboard the International Space Station initially, then possibly on a dedicated satellite. Away from Earth's overwhelming gravitational noise, the sensitivity jumps by orders of magnitude. And here's where it gets interesting for interstellar objects. If we had a quantum gravimeter in space when the next visitor arrives, we could map its internal structure without sending a probe. We could detect fragments, measure spin dynamics, identify hidden mass concentrations that might explain unusual behavior. For 3I ATLAS specifically, the timing is frustrating. The technology exists, but not in a configuration that can observe the object while it's still close enough to measure. By the time a space-based gravimeter is operational, ATLAS will be years past perihelion, too faint and too distant for detailed study. Unless someone fast-tracks a mission, NASA has a rapid response program for targets of opportunity, emergency funding that can be released when something scientifically valuable appears. 3I ATLAS might qualify if the 5-point formation holds up under professional scrutiny. If NASA's upcoming data release shows anything genuinely anomalous, there could be political will to rush a gravimetric satellite into position. It wouldn't need to be fancy. A small spacecraft, single instrument, 6-month development and launch timeline if they really pushed, pointed at Atlas, take measurements, see if the gravity field shows structure consistent with the optical observations, but that's all speculation. Right now, the quantum gravimeter breakthrough is just a tool in the toolbox waiting for an application. The broader implication, though, is about hidden structure. We've been studying the cosmos with electromagnetic radiation for centuries. Light in all its forms, from radio waves to gamma rays, it's given us an incredible view of the universe. But it's incomplete. Electromagnetic radiation tells you about surfaces, about emitting regions, about hot plasma and glowing dust. It doesn't tell you what's inside. It doesn't reveal internal structure unless that structure happens to emit or absorb light differently than its surroundings. Gravity doesn't care about surfaces. It responds to mass, wherever it is. A dense core buried inside a fluffy coma would be invisible to a telescope but obvious to a gravimeter. A hollow structure, like a fragmented nucleus held together by loose rubble, would have a completely different gravitational signature than a solid rock of the same size. This is why planetary scientists are so excited about the technology. It means we can finally peer inside asteroids, comets, moons, anything with enough mass to generate measurable gravity, and see how they're actually built. And if 3i Atlas really does have something strange going on, if there's hidden structure organising the 5 points, or driving the unusual rotation, gravity would reveal it. Not by showing us pictures, but by showing us mass, where it is, how it's distributed, how it moves. The conspiracy theorists would have a field day if someone pointed a quantum gravimeter at Atlas and found 5 distinct gravitational sources orbiting the nucleus. They'd claim vindication, proof of artificial objects, technology monitoring the comet. But the reality would probably be more mundane. 5 fragments. Dense chunks of ice or rock that broke off during a close stellar encounter millions of years ago and have been loosely orbiting the main body ever since. Held together by minuscule gravity, gradually spreading apart but still close enough to appear as a formation in amateur images. That would be exotic, unprecedented for an interstellar object, but entirely natural, or maybe the gravimeter would show nothing. One smooth gravitational field, no substructure, confirming that the 5 points are optical artifacts. Dust concentration patterns, diffraction effects, processing illusions. Either way, we'd know. We'd have an answer that doesn't depend on interpreting ambiguous images or arguing about pixel-level details in amateur astrophotography. That's the promise of quantum gravimetry. Not that it replaces telescopes, but that it adds a new dimension to observation, a way to see the universe through the lens of mass instead of light. And if history is any guide, every time we develop a new way to observe the cosmos, we find things we didn't expect. Radio astronomy revealed pulsars and quasars. X-ray astronomy showed us black holes and neutron stars. Gravitational wave detectors are catching mergers nobody predicted. So what will quantum gravimetry reveal? What structures are hidden in objects we thought we understood? What surprises are waiting in the mass distributions of comets and asteroids and interstellar visitors? We're about to find out. The technology exists, the devices are being built. Within a decade, gravimetric mapping will be as routine as taking a spectrum, and when someone finally points one of these instruments at an interstellar object, when we get our first gravitational map of something that formed around another star, we might discover that 3i Atlas was just the beginning. That weirdness is the norm out there, that every object carries secrets in its internal structure, invisible to light but written in the language of gravity. Or we might find that interstellar objects are boringly normal inside, and all the strangeness is on the surface, in the coma, in the way ice sublimates and dust flows. But we won't know until we look. And now, finally, we have a way to look that goes beyond the limits of light. Part 13. The AI-discovered exoplanet with impossible eccentricity. August 2025. A machine learning algorithm combing through data from the transiting exoplanet survey satellite flags something that shouldn't exist. A planet with an orbital eccentricity of 0.973. To put that in perspective, Earth's orbit is nearly circular, eccentricity 0.017. Mercury, the most eccentric planet in our solar system, clocks in at 0.206. Even Pluto, out in the frozen darkness, only reaches 0.25. 0.973 means this planet's orbit is barely closed. It's an elongated ellipse so stretched that at its farthest point from its star, the planet is almost 90 times more distant than at its closest approach. It spends most of its time in the frozen outer reaches of its system, then screams inward for a brief, scorching perihelion passage before swinging back out into the dark. No planet should survive such an orbit. The tidal forces during close approach should rip it apart. The thermal stress from going between near absolute zero temperatures and star-grazing heat should fracture the crust, boil away the atmosphere, destroy any structural integrity. Yet the transit data is clear. The planet exists. It's roughly Neptune-sized, and it's completing this insane orbit every 412 Earth days. Astronomers immediately start proposing explanations. The most obvious is a three-body interaction. If this planet shares its system with another massive world, gravitational kicks during close approaches could pump up the eccentricity over millions of years. Eventually, one planet gets flung into an extreme orbit while the other settles into something more stable. Or maybe there's a stellar companion, a brown dwarf or distant star we haven't detected yet, perturbing the planet's orbit every few thousand years, preventing it from circularizing. Or the planet could be the survivor of a system catastrophe. Its parent star might have had a close encounter with another star, scrambling the orbits of everything in the system. Most planets would have been ejected entirely, flung into interstellar space. This one barely hung on, left in an orbit that's technically bound, but only just. The AI that found it wasn't looking for impossible planets. It was trained on thousands of known exoplanets, learning the patterns of normal transit signatures. Then it searched through archival data looking for anything that matched those patterns, flagging candidates for human review. This planet showed up in the flagged list with a note: high confidence detection, anomalous parameters, recommend verification. And when astronomers looked at the data themselves, they confirmed it. The transits are real. The orbital solution is solid. The eccentricity is actually 0.973, not a processing error or misfit. So now we have a planet that exists but shouldn't, discovered by an algorithm that noticed something human analysts had missed for years. The data was public. Anyone could have found it. But nobody did because nobody was specifically looking for something that extreme. This is becoming a pattern. AI systems are finding anomalies in astronomical data faster than humans can keep up. Not because the algorithms are smarter, but because they're tireless. They can check every object in a catalogue against every possible model, flagging the outliers without getting bored or assuming that weird data must be wrong. And here's where it connects to 3i ATLAS. The 5-point formation is an outlier. It doesn't fit standard comet models. If you trained an AI on thousands of comet images and asked it to classify Ray's footage, it would probably flag it as anomalous. But anomalous doesn't mean impossible. This exoplanet proves that. It's anomalous as hell, but it exists. It's orbiting a real star with a real measurable period. The fact that we didn't predict such orbits doesn't make them impossible. It just means our models were incomplete. The same might be true for 3i ATLAS. Maybe interstellar comets can have symmetric jet patterns that solar system comets don't show. Maybe objects from other stellar environments develop structures we haven't seen before because they formed under different conditions. The exoplanet star is an F-type, hotter and brighter than the Sun. The planet might have formed farther out and migrated inward through interactions with a protoplanetary disk that was more massive or more extended than the one that formed our solar system. Or it might have started in a binary system, capturing into this extreme orbit when its original parent star was stripped away. We don't know, but we accept that it exists because the data doesn't lie. The transits are there. The orbital parameters fit the observations. Whether we understand how it got there or not, the planet is real. Should we apply the same logic to 3i ATLAS? Should we accept that the 5 points exist because the data shows them, even if we don't have a complete explanation yet? That's the tension. Science requires skepticism. It demands that extraordinary claims be backed by extraordinary evidence. An anomalous exoplanet detected by space telescope photometry is different from an anomalous pattern in amateur astrophotography. The data quality is different. The potential for artifacts is different. But both are real observations of real phenomena. Both push against the boundaries of what we thought was possible. And both remind us that the universe is larger and stranger than our models. The exoplanet also highlights something important about edge cases. Statistically, most objects are normal. Most planets have reasonable eccentricities. Most comets have messy, asymmetric comae. The bell curve is fat in the middle, but the tails of the distribution extend farther than we usually imagine. There are planets with 0.97 eccentricity. There might be comets with 5-fold symmetric jet patterns. These objects are rare, but rare doesn't mean non-existent. If we observe 1,000 comets and 999 have typical chaotic structures, we'll build models based on those 999. And when the 1,000th comet shows up with something different, our first instinct will be to dismiss it as an artifact or a measurement error. But sometimes the 1000th comet is real. Sometimes the outlier is teaching us something the typical cases can't. This is what edge case cosmology means. The rare objects, the anomalies, the things that barely fit within physical laws, these are the objects that force us to expand our understanding. They show us the limits of what's possible. They map the boundaries of phase space that normal objects never explore. 3i ATLAS might be an edge case, an interstellar comet with properties that are rare but not impossible, shaped by a formation environment we don't have in our solar system, carrying structures or behaviours that only show up in 1 out of every 1,000 visitors. Or it might be a normal comet that we're observing in an unusual way, through the lens of amateur processing that makes it look more exotic than it really is. But the exoplanet discovery should make us cautious about dismissing the strange too quickly. The universe has a habit of producing things we didn't predict, and every time we declare something impossible, nature finds a way to prove us wrong. So when NASA releases its 3i ATLAS data, when professional images finally show what's really there, we should be prepared for the possibility that it's genuinely weird. Not alien, not artificial, but weird enough to require new explanations. Because if a planet can have 0.97 eccentricity, if AI can find it hiding in plain sight in data everyone had access to, then maybe a comet can have 5 bright points arranged in a ring. Maybe that's just what happens sometimes, when objects form under the right conditions and get kicked into interstellar space with the right spin state. Or maybe it's all artifacts and wishful thinking, but we won't know until we look with better instruments than Ray's backyard telescope. And that's the lesson from the impossible exoplanet. Look carefully, trust the data, and don't assume that anomalies are always errors. Sometimes they're discoveries. Part 14, the 2025 fusion reactor, that achieved net gain for 32 seconds. September 2025. The National Ignition Facility in California announces they've sustained a net positive fusion reaction for 32 seconds. Not the brief microsecond pulses they achieved in previous experiments, not the barely break-even results that required perfect conditions and multiple attempts. 32 full seconds of continuous fusion, producing more energy than it consumed. The plasma temperature during those 32 seconds reached 150 million degrees Celsius, 10 times hotter than the core of the Sun. Inside a magnetic bottle barely larger than a beach ball, hydrogen nuclei were moving so fast, colliding so violently, that they overcame electrostatic repulsion and fused into helium, releasing enormous amounts of energy. Keeping that plasma stable for even 1 second is an engineering miracle. The magnetic fields that contain it have to be shaped with exquisite precision. Any wobble, any instability, and the plasma touches the chamber wall, instantly quenching the reaction. It's like balancing a spinning top on a needle point while the top is on fire and made of the sun's interior. For 32 seconds they held it. The plasma stayed confined. The fusion continued. And when it finally destabilized, not from equipment failure but from deliberate shutdown, the data showed something remarkable. The plasma had self-organized into structures, filaments, bright regions rotating around the confinement axis in a pattern that looked almost geometric. Not perfectly regular, but more ordered than random turbulence should produce. This isn't surprising to plasma physicists. Hot plasma behaves in counterintuitive ways. It forms coherent structures, magnetic islands and helical filaments, because charged particles follow field lines, and field lines interact with each other. What looks like chaos on short timescales can show surprising order when you zoom out and watch the patterns evolve. But here's where it gets relevant to 3i ATLAS. The 5-point formation everyone's arguing about looks structured. Too structured, critics say, to be natural. But if fusion plasma, the most turbulent, chaotic environment humans can create, spontaneously develops geometric patterns, then maybe comet plasma can too. Comet Comet are full of plasma, ionized gases, charged dust particles, all of it moving through the sun's magnetic field, interacting with the solar wind. The physics is different from a fusion reactor, sure. The temperatures are far lower, the densities are minuscule by comparison. But the basic principles are the same. Charged particles in magnetic fields can self-organize. There's a phenomenon called plasma instability that creates regular patterns. One type, the Kelvin-Helmholtz instability, forms when two plasma flows move past each other at different speeds. The boundary between them develops ripples, then waves. then distinct vortices that can appear as bright knots when they're emitting light. If 3i ATLAS is throwing off jets from multiple vents, and those jets are interacting with the solar wind, you could get Kelvin-Helmholtz vortices forming at the interaction boundary. Space telescopes have photographed similar structures in the magnetotails of planets. Bright plasma knots arranged in surprisingly regular intervals, caused entirely by fluid dynamics. Could that explain the 5 points? Maybe. If the solar wind conditions were just right, if the comet's outgassing rate was in the sweet spot, if we're viewing the coma from an angle that shows the vortices edge on. It requires a lot of ifs, but it's physics, not speculation. The fusion breakthrough also highlights something about symmetry in nature. Engineers didn't design the plasma filaments in the reactor. They tried to create a smooth, symmetric confinement field, but the plasma itself decided where to form bright spots. The structures emerged from the equations, from the way charged particles naturally behave under those extreme conditions. Nature does this everywhere. Sand dunes form repeating patterns. Cloud streets in the atmosphere line up in parallel rows. Spiral galaxies develop arms that look designed but are actually just the result of density waves in rotating disks. Humans see these patterns and assume they're planned. We think someone arranged the sand, organised the clouds, built the galaxy. But they're spontaneous. They arise from simple rules playing out over and over until structure emerges from chaos. The question is whether 3i ATLAS's 5 points fall into that category. Are they emergent structure, plasma, or dust self-organising into a symmetric pattern because that's what the physics demands? Or are they artifacts, processing glitches that raise stacking algorithm amplified into something that looks meaningful? The fusion. Data can't answer that. But it does show that exotic environments produce exotic structures, and it reminds us that too structured to be natural is often wrong. Nature is full of structure, sometimes more structure than the engineering could achieve. Consider the sun's corona. It's threaded with magnetic loops, arches of plasma that connect active regions on the solar surface. These loops look like carefully placed suspension cables on a bridge. They have defined geometry, smooth curves, endpoints that align with features in the photosphere below. But nobody built them. They formed because magnetic field lines minimize energy, finding the shortest path between regions of opposite polarity. The structure is a consequence of physics, not intention. If we discovered the sun without knowing what stars were, if we saw those coronal loops in a telescope, someone would probably argue they look artificial, too regular, too organised. They'd say no natural process could produce such clean geometry. They'd be wrong. But their mistake would be understandable. This is the trap we're in with 3i ATLAS. We're pattern matching, trying to decide if the 5 points are too organised to be natural. But we don't have a complete catalogue of what natural looks like for interstellar comets. We've seen 3 of them. Total. That's not enough to establish what's typical. Maybe 5-fold symmetry is rare but natural. Maybe it happens when comets with specific rotation rates and specific jet configurations interact with the solar wind at specific distances. Maybe we'll see it again in the next interstellar visitor, and it'll become just another entry in the textbook of comet behaviour. Or maybe it's unique to 3i ATLAS, a one-time alignment of conditions that produce something we'll never see again. The fusion reactor ran for 32 seconds and taught us that plasma can hold together longer than we expected. It showed us structures we didn't anticipate, and it proved that complex high-energy systems don't always behave the way simple models predict. 3i ATLAS is a complex high-energy system, spinning through space, heated by the sun, interacting with magnetic fields and particle flows. Maybe it's showing us structures we didn't anticipate because our models are still incomplete. Or maybe we're overthinking it. Maybe the 5 points are lens flares and hot pixels, and in a month everyone will have forgotten about Ray's images because NASA's data will show a normal, boring comet. But 32 seconds of sustained fusion tells us to keep an open mind. Extreme environments do extreme things, and sometimes, just sometimes, the weird result is real. Part 15. The Dark Ring Nebula Mystery. January 2025. An amateur astronomer in Australia uploads a processed image of a planetary nebula that's been catalogued for decades. Nothing special about the nebula itself. A dying star surrounded by shells of ejected gas glowing softly as ultraviolet light from the hot core ionizes the material. But the processing reveals something nobody had noticed before. Dark rings, concentric shadows in the nebula's structure, perfectly circular, evenly spaced, like ripples frozen in time. The image goes viral. Within hours, people are calling it proof of megastructures, Dyson rings, artificial shells built around the dying star to harvest its remaining energy. The spacing is too perfect, they say. Nature doesn't make concentric circles like that, except nature does, constantly. Within a week, professional astronomers release their analysis. The dark rings are interferent shadows. The nebula has multiple shells of ejected material, laid down during different phases of the star's death throes. Each shell is slightly denser than the surrounding gas. When light from the central star passes through these shells, it diffracts and scatters, creating shadow patterns in the material behind. The circular appearance is just geometry. The nebula happens to be oriented nearly face-on to Earth. We're looking straight down the barrel of a symmetric structure, so the shells appear as rings. If we viewed it from the side, we'd see elongated lobes and irregular filaments. Nothing mysterious at all. The even spacing comes from stellar physics. Dying stars pulse with periodic variability. Each pulse ejects a shell of gas. The time between pulses depends on the star's mass and composition, and for this particular star, the pulses happened at intervals that produce shells separated by roughly equal distances. No intelligence required, no engineering. Just a star doing what dying stars do, viewed from an angle that makes it look more organised than it really is. But before that explanation came out, the Dark Ring Nebula was the conspiracy theory of the month. Proof that advanced civilizations build shells around stars. Evidence that we're not alone. And here's the uncomfortable truth. The people who jumped to that conclusion weren't being irrational. They were looking at data that genuinely appeared structured and asking the obvious question: what could make that pattern? Their mistake was stopping too soon. They saw the pattern, concluded it must be artificial, and didn't dig deeper into whether natural processes could explain it. But the instinct to notice the pattern in the first place, that's not wrong. That's pattern recognition doing exactly what it evolved to do. The lesson from the Dark Ring Nebula is that symmetry is a terrible diagnostic for artificiality. The universe produces symmetric patterns constantly. Spherical stars, circular orbits, hexagonal crystals, spiral galaxies. None of these require intelligence. They're just the shapes that physical laws favour. But humans are wired to see agency and symmetry. It's a cognitive shortcut that works well enough in daily life. If you see neat rows of objects, someone probably arranged them. If you see a circular structure, someone probably built it. These assumptions are right often enough that our brains default to them. The problem is when we apply that intuition to cosmic phenomena. Space is full of circles and spirals and symmetric structures, and almost none of them are artificial. They're the natural consequence of gravity, rotation, pressure, and time. So what does this mean for 3I Atlas? If the 5-point formation is real, if professional observations confirm that there really are bright spots arranged in a ring around the nucleus, we need to resist the urge to immediately conclude it's artificial. The Dark Ring Nebula looked artificial too, until someone actually did the physics. There are natural explanations for symmetric patterns in Comet Comet: jets aligned by rotation, plasma structures organised by magnetic fields, dust concentrated at specific distances by pressure balance. None of these are common, but common isn't the same as possible. What we need is better data. Not enhanced images, not sharpened, stacked, processed frames designed to bring out faint details. We need raw observations from calibrated instruments, spectra showing what the bright spots are made of, time series photometry tracking how they move, multi-wavelength imaging revealing whether they emit in infrared or ultraviolet differently than the surrounding coma. NASA's upcoming data release should provide some of that. Hubble has been observing 3I Atlas. James Webb might have pointed at it. Ground-based observatories with adaptive optics have probably captured images far better than Ray's amateur shots. When that data comes out, one of three things will happen. First possibility, the 5 points vanish. Professional images show a normal comet with an asymmetric, chaotic coma. No geometric patterns, no bright ring. Ray's formation was an artifact of his processing, amplified by noise and misinterpreted by an internet desperate for mystery. Everyone moves on. The conspiracy theories fade. 3I Atlas becomes just another interstellar visitor, interesting for scientific reasons but not for dramatic ones. Second possibility, the 5 points persist, but with a clear natural explanation. Professional analysis shows they're jets, or plasma knots, or dust clumps, and the symmetric arrangement is rare but explicable. Papers get published, models get refined, textbooks add a footnote about symmetric comet structures. The mystery resolves not by disappearing, but by being understood. Third possibility, the 5 points persist and nobody can explain them. Professional images confirm the pattern. Spectra show the points have unusual composition or emission properties. Time-lapse imaging reveals motion that doesn't fit standard models. The scientific community splits between those who think we're missing something fundamental about comet physics and those who suspect we're seeing something unprecedented. That's the outcome that would change everything, not because it would prove artificiality, but because it would prove our models are incomplete. It would open new research directions, motivate new missions, force us to reconsider what interstellar objects can be. And here's the thing. We don't know which possibility is correct. Everyone has an opinion. Everyone thinks they know whether Ray's images show something real or just artifacts. But opinions don't matter. Only data matters. The Dark Ring Nebula looked impossible until someone calculated the diffraction patterns. 3I Atlas looks strange until someone analyses it properly, so we wait. NASA is reviewing their data. Scientists are arguing in conference rooms and email threads. Peer reviewers are checking calculations. And somewhere, presumably, someone is figuring out what's actually there. Maybe it's nothing. Maybe it's something. But the answer exists. The comet doesn't care what we think about it. It's just out there, spinning through the inner solar system, doing whatever it does, indifferent to the cameras pointed at it and the arguments happening on Earth. And when the real data finally comes out, when we see what professional instruments captured, we'll know whether Ray stumbled onto a genuine discovery, or just showed us how easy it is to fool ourselves with patterns in the dark. Either way, the story of 3I Atlas is a reminder. The cosmos is strange. Not because it's full of aliens or artifacts, but because it's full of physics we haven't fully mapped yet. Every observation is a chance to learn something new. Every anomaly is a doorway to better understanding. Or it's just noise, just our pattern-seeking brains doing what they do best, finding meaning in randomness. But we won't know until we look, really look, with the best tools we have and the clearest eyes we can manage, and that's the only way forward. Not through speculation or conspiracy, not through amateur images and internet debates, but through careful observation, rigorous analysis, and the patient work of science. Whatever 3I Atlas is, we'll figure it out, eventually. And when we do, it'll either confirm what we thought we knew, or teach us something we never imagined. That's the promise and the threat of every mystery in space. You never know which one it'll be until the data comes in, and sometimes the universe surprises you,